Okay, our next step will be to be describing these graphs. And it's the second page on your notes. See, this first page was that. It's the second page where you start with distribution right there. So that's where we're at right now on the notes. And when you're describing a distribution, make sure to always include CUSS, C-U-S-S, and you also include the context and the units. Be sure to always include a picture as well. Now, CUSS is how you describe the picture. You start with describing its center, then you look for unusual features, and you look for the shape of the graph, and you look for how spread out the graph is. So that's C-U-S-S, CUSS. If you had to pick a single number to describe all data, what would you pick? This would be the center of the distribution. You're looking for like the middle area. And there's a lot of ways to describe that. One of the numbers, it's one number that represents the expected value or tendency of the data, like where the value is centered towards. It's usually easy to find it if it's like unimodal or symmetric. It's right in the middle. On the other hand, it's not as easy to find it if the data is kind of weird and skewed in one direction. It's a little harder to find the middle. The first measurement we're going to look at is median, which is the middle value. It's the value with exactly half of the data values below it and half above it. So it's the middle data value that divides the histogram into two equal variables. See, like right in the middle between the yellow and the purple right here is the median, right at like 7.0. It has the same units as the data, and if you have an even amount of data, you will average the two middle values. You probably did this like, back in middle school. I'll give you an example of like some data values where you find the median. Say we had these four values. 1, 2, 3, 4. Now there's no middle value with 4, right? So what you do is you chop right in the middle, like right there between 2 and 3, and you take the average of those. What's the average of 2 and 3? 2.5, and that is the median. You can like do that over to the side, and that's the median of 1, 2, 3, 4. Because it's 2 plus 3 divided by 2 to get the average. 5 divided by 2 is 2.5. The mean is the average value for all of the data, found by adding all of them together and dividing by the number of values. So it's better for symmetric distributions. Like when your graph looks symmetric, the mean is the best thing to use. And that's pretty simple, right? Everybody knows how to find the mean. Now the mode is the value that's found most often in the data. Like what if we had this data? 1, 2, 2, 3, 4. What would the mode be? The mode would be 2 because it happens twice. So that it would be the mode. Mode equals 2. And that's called the mode. So here's an explanation of the mean. This isn't that important. I think everybody knows how to calculate mean. You just add them all together and divide by the total number. The total number of data that you have. And they use the Greek letter sigma for sum. So this is just add them all up, right? And then divide by the total number of values. The mean feels like the center because it's the point where the histogram balances. But you got to be careful because if there were an outlier, like way out here, like say there was a magnitude 50 earthquake way out here, that would destroy the whole earth, but you get my point. Like way out here, it would cause this mean to kind of shift to the right. And the mean would be way over here somewhere. So like outliers and like skewed data can cause the mean to be off, and we'll get more on that later. Because the median only considers the order of the values, it is resistant to like an extraordinary large or small number, like that 50 magnitude earthquake would have pulled the mean way out of the way. It ignores the big ones or the small ones, ignores their distance from the center. So to choose between mean and median, you look at the data. If it looks symmetric and there's no like big numbers way on the outside, mean's a pretty good value to use. However, if it's like skewed or it's got big outliers, you want to use median. Do any unusual features stick out? So we did the C, now we're on the U, unusual. So what they mean by unusual, are there any outliers? Like what if there were that 150 magnitude earthquake way on the outside? That would be called an outlier. That stand away from all the other data. And are there any gaps? And usually outliers will be out there and there'll be a gap between all the other data and the outlier. So if there's any gaps or outliers, that's unusual data in a graph. And you always look for that, and you always talk about it when you're talking about a graph. Here's some unusual things. If there's multiple modes, and what they mean by mode, remember mode is one that happens the most often. If you got, well, we'll get to that in a little bit. I'll show you an actual example of it. And if there's any clear outliers, and you're reporting like mean or standard deviation, you report the outliers. You always talk about outliers on these as well. So if multiple modes would be unusual, and they call that bimodal. So look at this one and see if there's anything unusual. This is unusual. There's outliers over here at 2.6. And there's also a gap, and that is an outlier. So there would be an outlier and a gap, and those are both unusual, right? What is the shape of the distribution? This is the next S. We did C and U, now we're on S shape. Does the histogram have a single central hump or several humps? The modes, the big peaks in the graph. And is the histogram symmetric or skewed? And does it have any unusual features? So let's take a look. So the spread is how many they call it humps or modes. Humps in the histogram are called modes. And it's big peaks in the graph. If it has one main peak, it's unimodal, which is the one that happens most often. Like in normal symmetrical data, it'll be unimodal. If it has two peaks, it's bimodal. If it has three or more, it's multimodal. And if it has no peaks, it's called uniform. It's like flat and doesn't ever peak. So this is bimodal. There's a peak right here and a peak right here. This is what a bimodal graph would look like. It has two peaks on it. This one has no peak. See, none of these stick out way farther than the other ones. So that's called uniform. A good example of that would be if you rolled a six-sided die a bunch of times, every value should happen about the same amount of times, and the graph will be kind of flat. And that would be uniform. And next thing we look at is symmetry. Does it have symmetry to it? This is symmetrical, roughly symmetrical. Like right here. That is mostly symmetrical. It's not 100% symmetrical, but I would call this symmetrical. And symmetrical means you can almost fold it onto itself and split it in the middle and fold it, and you almost can. See, it's very similar. And so that would be called a symmetrical graph. Now, the thinner ends of a distribution are called tails. If it starts to tail off like this right here, the histogram is said to be skewed to the side of the longer tail. So let's take a look at this one on the left. See how that goes down like that, and it has this long tail going this way? This would be skewed to the left. So because it has a tail going to the left, right? So that is left skewed. And this, see, it has a tail going to the right. That would be right skewed. So that's what a skewed graph looks like. It tends to dip down on it with a tail in one direction or the other. So right-tailed has a tail on the right. Left-tailed has a tail on the left. They can call it left-tailed or left-skewed, right-tailed or right-skewed. They mean the same thing. Next thing they look at is how spread out the distribution is. This is variation. And statistics represents the variability in the data. Are the values of the distribution all tightly clumped together? Or are they more spread out? This is important when you're looking at a graph, how spread out it is. And you always use a measure of spread to describe a distribution. And the most powerful spread measurement is standard deviation, which takes into account how far each data value is from the mean. A deviation is a distance that a data value is from the mean. That's what deviation means. It's how far away you are from the normal. And since all the deviations together would be 0, since adding all deviations together would total 0, we square each deviation to find an average of sorts. Because you can be like far away to the right or far away to the left, and they're both far away, so that's why we end up squaring in the calculation. Now I'm going to show you this calculation right here, but we're never actually going to do a calculation on a test or anything, but this is how they get the data. Like say we had 1, 2, and 3 as our data, right? What's the average right there? The mean is 1 plus 2 plus 3 is 6 over 3, which is 2, right? The mean is 2. So to find the standard deviation, the variance, the s squared, you would do y minus the mean. This means mean, the y with the bar above it. So it'd be 1 minus 2 squared plus, and then 2 minus 2 squared plus 3 minus 2 squared over n minus 1. There were 3 terms, 3 minus 1. So what's the standard deviation? 1 minus 2 squared is negative 1 squared. That's 1 plus 0 plus 1. So the top is equal to 2 and the bottom is equal to 2. So 2 over 2, your standard deviation is 1 on this one. The variance is 1. So the variance plays a role later. You will not need to know how to calculate it like that. We may do like one example of calculate just to show you how they find it. And see how each of these are telling you how far away from the mean you are? Like 1 is 1 away from the mean, 2 minus 1, right? 3 is 1 away from the mean, which is 2. It's just telling you how spread out the data is. The standard deviation is the square root of that. This is the key calculation here. This is the one you're always going to be using in this class for the most part, is the standard deviation. You take the square root of it. And like I said, we're almost never going to calculate this by hand. It will always be in a calculator or on the Statlet app. So I wouldn't worry about calculating it that much. We'll always just be able to calculate it with the Stat app or the calculator. Another calculation they use to talk about how talk about the spread is the range, like the max minus the min. You've probably seen this one many times before. Now, range can be messed up if there's some huge outlier on the outside. Like say I had this data. 1, 2, 2, 3, 4, 4, 1,000. Now, the range would be what? Max minus min, 1,000 minus 1. The range would be 999. But that doesn't really tell us the whole story, because this 1,000 is throwing that off and making the range huge. Most of the data is between 1 and 4. So 1 and 4 is more like a true range, like 3. But this is throwing it off, and that's why range is bad if you have like a very large or big number that's not part of the normal data. That's why they use interquartile range. So if we did that again, 1, 2, 2, 3, 4, 4, 1,000. Let's do that. 1, 2, 2, 3, 4, 4, 1,000. Now the interquartile range is the middle half. You know, it would be like these right here, this middle half. But we're going to get to the calculation of it. But what it does is, since it's looking at the middle half, it cuts out like big numbers like 1,000. And it's much more useful. And we'll get to how to calculate the interquartile range later. So interquartile range is better for being able to calculate if you have like a big outlier. It's used with the median. So a quartile divides it up into 4 equal sections. The first quarter, the third quarter, the second quarter, which is the median, the middle, and the third quarter. And then the fourth quarter would be the last, right? Like all the data, basically. The 100th percentile. So the difference between the quartiles is the interquartile range, the third quarter and the first quarter. So the 75th percentile, like where 75% of your data stops, minus the 25th percentile, right? Where the first quarter of your data stops. And that is called the IQR. And it's Q3 minus Q1, and we will always have a calculator to get that for us usually. So the IQR contains the middle 50% between the 25th and 75th. In this graph, it's this yellow area. 25% of the data is this blue out here. The middle 50% is this yellow, and the last 25% is this blue out here. So this middle is the IQR, the interquartile range, the middle 50%. That's what IQR means. It's the middle 50%. And you'll really get to see it when we actually do some calculations for it. Now, you're going to find something very common here called the 5-number summary. And let me show you where that is on your notes, because we just bounced a little bit. If you go down to where it says boxplot display on your notes on the third page, so this is the second page right here, and go down, and third page you'll start talking about boxplot right here, the 5-number summary reports. Because we're about to start talking about the summary reports right there. All right, the 5-number summary of a distribution reports its minimum, its maximum, the first quartile, the third quartile, and the median. So it's telling you all the points in the graph, like the very beginning, the lowest point, and then the first 25%, and then the middle 50%, which is the median, and then, so, you know, the lowest, oh, let me use my pen. The lowest point, the minimum, oh. So the minimum, the lowest point on the graph, and then the first quartile, the 25%. So this is at 0%, the lowest, and then the median at 50%, and then the quartile 3 at 75%, and then the maximum is bigger than 100% of the data. It's the biggest point on the graph, and that is called the 5-number summary of statistics. You'll see this all the time in statistics. A box plot is a good way to show it. And actually, we're going to get into box plots on the next video because this video is running pretty long. So I will stop here and we will talk about box plots on the next video.